Okay, this is an extra lecture on number systems. In every class I teach, with the exception, I believe, of CIT 105, which is the general class that most people, if not everybody, has to take, I like to do a lecture on number systems. The reason I do that is I believe if you're a CIT or CS major or somebody studying network, that it would be beneficial to you and important to know that. Now, typically I do this lecture in person. I actually did it last night in one of my in-person classes. And I think it probably goes a little better if we're kind of interacting back and forth, but I'll do the best I can on here to do that. And the way I always start this lecture is, why is 123 123? And the answer is not just because it is. So we'll be thinking back to maybe middle school, elementary school, talking about some math that we would have done in that time frame. But what I do is I kind of sidetrack and I start out asking, what base do we normally work in our day-to-day life? And usually one or more students will say decimal or base 10. And then I'll ask, why do we work in base 10? And typically somebody answers. Last night I didn't have anybody answer, but I hold up 10 fingers and say we work in base 10 because we have 10 fingers. So that's why we do that. Now then, in base 10, and I try to teach this so that no matter what base we're working in, you should be able to recreate this. So the one question I always ask when we're talking about different base is, how many digits do we have? And the answer is 10. No matter what base we're working in, whatever base it is, the answer to how many digits do we have is always the same as the base. Then I will say, okay, in the base we're working in this case base 10, what are the actual digits we have? And the digits we use in the day-to-day base 10 world is 0 through 9. So how many digits do we have? Always the base. What are those digits? 0 through 1 less than the base. And that's true for any number system that we might be working in. The next thing I go back and do, trying to answer the question, why is 123 123? And the answer is because each of these positions have what we will refer to as weights. So sometime with a little prompting, students will come back and say, oh, this is the ones, this is the tens, this is the hundreds, next we would have the thousands, etc. So then I ask them, okay, why are the ones and why are the tens the 10 when we're working in base 10? And typically students do not remember why that's the case. But to get the weight of the digits, we put the base we're working in, and then we raise those to successive powers starting at 0. So 10 to the 0th, 10 to the 1st, 10 to the 2nd. If we had another digit, it'd be 10 to the 3rd. So anything to the 0th power is 1. So no matter what base we're working in, the rightmost position is the ones, or has a weight of 1. The next position is the base raised to the first power. Anything raised to the first power is itself. So 10 to the first is 10, so that position is the tens. The next position is 10 squared, or 10 to the second power, that's 100. And 10 to the third is 1,000. Once you get these two positions, you can say this is 1, this is the base, and then you can just start multiplying by the base. So 10 times 10 is 100, 100 times 10 is 1,000, etc. Because basically 10 to the third is 10 to the second times another 10. So once you get the first two digits, you can go through and do that. So the reason 123 is 123 is because we have 100, we have 2 tens, and then we have 3 ones. And if you add that together, we end up with 123. So that's why 123 is 123. So I like to go through and talk about that, before we start talking about other bases. So computers work on binary, which is also base 2. And since computers work on binary, that's why your textbook may talk about it and why we're going to start with it. So I told you that I would always ask, how many digits are there? Sorry, the writing's not so great on here. So how many digits do we have? Well, we're working in base 2, so the answer is 2. And what are the digits that we have? That would be 0 and 1. So 0 to 1 less than the base. So that's a couple of facts that we need to know. Now, personally, when we're doing number conversions, I think that going from some arbitrary base, in this case base 2, to base 10 is the easiest thing to do. So, for example, let's say that we had 101101, and we're told that that's a base 2 number, which is represented by a subscript. And I ask you, what is that in base 10? So you will have some homeworks that have number conversions, and there will likely be number conversions on your midterm exam. I don't know if there will be on the final or not, but there could be. So anytime we do this, the first thing we need to do is figure out the weights of each position. And you will start shortcutting this when you start feeling comfortable with this. But we take the base, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5. And if we go back and do that, so we have the zeros, the 1s, the 2s, the 4s, the 8s, the 16s. See, I got out of sync somewhere here. 8s would be there, 16s, and 32s. So those are the weights of our digits. So then what I ask the student is I go through and say, how many 32s do I have? And the answer would be 1. Then I go through and I say, how many 16s do we have? And of course the answer is 0, looking at the number up here. Then I ask, okay, how many 8s do we have? The answer is 1. How many 4s do we have? Looking up here, it's 1. How many 2s do we have? The answer is 0. And then finally, how many 1s do we have? And the answer is 1. So the weights are coming from down here at the bottom where we calculated them. And then how many of each we have are coming from these positions here in the numbers. Now, if you add this up, we have 32 plus 0 plus 8 plus 4 plus 0 plus 1. That's just going through and doing the calculations. Now, one of the next steps you'll do is 0 times anything is always 0. So, you probably stop pretty quickly even putting those zeros down there. And then if you add these all up, you should get 45 base 10. So 11, let me start again. 101101 in binary is 45, or how you would represent 45 in binary. Okay, now still working in base 2, let's go the other way. That is, we have a base 10 number and we want to convert it to base 2 for some reason, maybe to show how it would be represented in memory on a computer. And this example is going to be, what is 50 base 10? What is that in base 2? Now, there's a couple of different ways we can do this. A lot of times your book will talk about what's called the subtraction method. I had one student last night who had done this, and he explained the process, and I said, yes, that's the subtraction method. But the method I like to use is the division method. I think you make less mistakes that way. And one of the things I do is I tell my students, okay, we're going back to 3rd grade math. And somebody real quickly tell me what 5 divided by 2 is. And invariably somebody will say 2.5. And I'll say, you did not know about decimals in 3rd grade. And then they would say, oh, 2.5. And I'll say, you didn't know fractions most likely in 3rd grade. How did you do math like that in 3rd grade? And sometimes the student come up with it, sometimes they won't. But we basically do something that's referred to as integer arithmetic. You know, your teacher puts 5 apples in front of you and says, how many sets of 2 can you take away from this? And your answer is 2. And how many apples do you have left? Well, if you started with 5, you took 2 sets of 2 away, or 4 apples, you're left with 1 apple. So the answer is 2 remainder 1. So that's called integer arithmetic. So basically what we do is we start with the number in base 10, and then we divide by the base we're converting to. So since we want to go to base 2, we would divide by 2. 50 divided by 2 is 25. You know, how many do we have left over? 0. It divides evenly. 25 divided by 2 is 12. How many do we have left over? 1. 12 divided by 2 is 6. How many do we have left over? 0. 6 divided by 2 is 3. Again, remainder 0. 3 divided by 2 is 1 with a remainder of 1. And then I'll tell my students, I'll go really quick, 1 divided by 2 is. And for some reason, students may have trouble with this. If they do, it's always the last step where the bottom number is larger than top. Sometimes they'll say 2, sometimes they'll say 1. But, you know, I'll go back and say, you have 1 apple. How many pairs of apples can you take from 1 apple? The answer is 0. How many apples do you have left? You have that 1 apple still. So it is 0, remainder 1 in this case. Once you get to 0 down here at the bottom, you stop the process. You then look at the remainders in the reverse order generated. So that would be 1, 1, 0, 0, 1, 0, and we were converting to base 2. So that would be your answer. So that's the division method. Now, in the case of the subtraction method, I'll just talk about through that really quick. A lot of times we talk about a byte, which is 8 bits. And each of these positions have weights. The last one, since we start 2 to the 0, is 2 to the 7, which is 128. So basically what you do is you say, how many times can I take 50 from 128 from 50? I can't. How many times can I take 64 from 50? I can't. How many times can I take 32 from 50? Well, I can do that once. And I have 18 left over. How many times can I take 16 from 18? Well, I can take it once, and if I take 16 away from that, then I'm looking at 2. How many times can I take 8 from 2? None. How many times can I take 4 from 2? None. How many times can I take 2 from 2? Once. And then that goes to 0. How many times can I take 1 from 0? I can't. So you'll see, with the exception of the leading zeros right here, that I got the exact same answer. So whichever makes the most sense to you. Like I said, I personally provide the information on the division method and tell students I prefer that. For whatever reason, I decided to talk through the division method, probably because one student explained it to the class, and so therefore I explained it to you. So whatever method works for you is perfectly fine. Now then, the next base I want to talk about is base 16. Base 16 is also referred to hexadecimal. It's kind of a long name, so sometimes it's referred to as hex. But that's what we're going to talk about next. Base 16 is very, very common in computers. The reason being is a hexadecimal digit can go in 4 bits from 0000 to 1111, so it fits really nicely in 4 bits. If you put 2 hex digits together, you can very easily and concisely represent the contents of a byte. So, back to our standard questions. How many digits do we have? Well, we're working in base 16, so the answer is 16. Now, sometimes students, some kind of know this, some don't. Sometimes there's some arguments. I haven't had an argument lately, but used to. People wanted to argue with me. The digits are 0 through 15. Now then, the problem we have with that, and what some people have seen or know, is if I have a string of digits and I have a 1, 5 in that string, do I mean a 1 followed by a 5, or do I mean 15? So there can be some confusion if we allow multiple characters to represent a single digit. So what happens is, this is problematic. So we say we have 0 through 9, and then we use A, B, C, D, E, and F to represent 10, 11, 12, 13, 14, and 15. So that way there's no confusion. So you just start at A, and you use however many digits. If we're working in base 20, you would go G, H, I, J. Yeah, 4 more digits on there. So like I told you before, I personally think going from a base 16 in this case, to base 10 is the easiest thing to do. So we'll do an example of that first. So we might have a hexadecimal number, which is 1AE, base 16, and we want to know what does that equal in base 10. So first thing we need to do is figure out the weights. So this is 16 to the 0, 16 to the first, 16 squared. Have to get ahead of myself here. So anything to the 0th power is 1, anything to the first power is itself, and then, I'll ask students and they'll think about it, and, ultimately 16 squared is 256. I'll ask them what 256 cubed is, and the answer is 4,096. And if we go one more, it's like 65,536. So the math gets pretty big pretty quick. So I try not to give you anything terribly complicated. So then I'll ask my students, how many 256s do I have? And they'll look at the number and they'll say 1. Then I will say, okay, how many 16s do I have? And they may have to think a little longer, maybe count on their fingers, but A is 10. And then I will say, how many 1s do we have? Well, we have an E there, and E is 14. So this becomes 256 plus 160 plus 14, which should equal 430 base 10. So other than the math maybe being a little bigger, the process is exactly the same. Okay, so what if we have a base 10 number and we want to go to base 16? So the example I have is we have 714 in base 10 and we want to know what that is in base 16. So what do we divide by? Well, we're going to base 16, so that is what we divide by. I'll do this first one for you. 714 divided by 16 is 44, remainder 10. I'll then ask the students what is 44 divided by 16. After a little thought, they'll come up with 2 pretty quickly. And then last night I got about 4 different answers for what the remainder is, but the correct remainder is 12. And then again, how many times can we take 16 from 2? None. What is the remainder? It is the 2 that we started with. We then, just like before, take the remainders in reverse order. So the first one is 2, 12 is C, and 10 is A. So as we go through and do the conversion, we need to convert to the appropriate hexadecimal digits, which again is 0 through 9, A, B, C, D, E, F. So that's your first introduction possibly to working in different bases. Again, we work with base 2 because that's what computers understand, bunch of 1s and 0s. We work in base 16 because a lot of times that's a base that computer programmers work in. I will save this for another time, another lecture, but another very popular base to work in is base 8. So this is your first introduction. At some point I'll come back. We'll probably start with base 8 and then maybe do some other conversions as well.